We welcome you again to the History of AI podcast.
For episode 3.
Neural networks.
Yeah.
The brain behind AI.
Yeah, today we're diving deep into neural networks.
You know,
The engine powering the AI revolution.
we're going to unpack how they work,
Right.
where they came from.
Their impact on tech and society.
Get ready for some aha moments.
Yeah, for sure.
As we uncover those fascinating parallels
Right.
between these digital brains and our own.
So I've been exploring how neural networks take inspiration
Okay.
from the structure and function of the human brain. It's incredible.
What'd you found?
The parallels.
Yeah.
Like biological neurons in our brains,
Right.
they communicate through electrical signals,
Uh-huh.
and artificial neural networks, or ANNs.
ANS.
Yeah, they use these interconnected nodes to process information.
So it's like a digital echo of our
Sure.
own biology.
Exact.
So those nodes are basically like artificial neurons.
Exactly.
Uh-huh.
And just like biological neurons fire signals based on the input they receive. Right.
Artificial neurons calculate weighted sums of their inputs.
You got it.
Yeah.
Okay, so they're mimicking that basic neuron behavior.
Uh-huh.
What about those connections between neurons?
Right.
You know, the synapses.
The synapses.
How are those represented in ANNs?
That's where connection weights come in.
Okay.
Think about it this way.
Okay.
In the brain, synapses get stronger or weaker with use.
Right.
Well, ANNs adjust these connection weights during training to mimic that learning process.
So it's capturing that plasticity, the
Yeah.
brain's ability to change and adapt.
Precisely, through a
Ah.
process called backpropagation.
Uh-huh.
The network updates its weights based on the errors it makes. It's constantly refining its connections
Right.
to improve its performance.
So kind of like our brains do as we learn new things.
Exactly like that.
That's fascinating.
Yeah, it is.
So even though ANNs are simplifying
Right.
the incredible complexity of the human brain,
Yeah.
they're still holding on to that core idea of learning through connections. Right?
Let's zoom out a bit.
Okay.
What's the basic structure of a neural network?
Okay, so picture it as a layered architecture.
Okay.
It's a carefully organized system.
Huh?
You have your input layer, which takes in raw data.
Raw data.
Yeah, and this could be anything.
Okay.
Pixel values from an image.
Right.
Words in a sentence.
Uh-huh.
Even stock prices.
Wow.
Then you have your hidden layers,
Okay.
where the magic really happens.
Hidden layers. That sounds mysterious.
It is a little bit.
What goes on in there?
Think of them as the processing units.
Okay.
Each hidden layer transforms the data,
Right.
extracting features and patterns.
Hmm.
Deep networks can have many hidden layers.
Many.
And the more layers, the more complex the patterns they can learn.
So it's like each layer is building on the previous one,
Yes,
extracting higher and higher levels of information.
exactly.
Okay.
It's like building a tower, each layer adding complexity to the structure.
Right.
And finally, you have the output layer, which gives you the final result.
Okay.
This could be a classification, like
What?
cat or dog,
Right.
a prediction of a stock price,
What?
or even a piece of generated text.
So we've got this data flowing through these layers, but you mentioned neurons earlier.
Yes.
Where do those fit in?
Each of those nodes in the layers is an artificial neuron.
Okay.
It takes the weighted sum of its inputs,
Right.
adds a bias,
Okay.
and then applies an activation function.
Hold on. Activation function. What's that all about?
Activation functions are crucial.
Okay.
They introduce nonlinearity,
Okay.
allowing the network to capture the complexity of real-world data. Without them, the network could only model linear relationships,
Okay.
which would be way too simplistic for most problems.
So it's like adding a layer of sophistication
It is.
to neurons' calculations.
Exactly.
Got it.
There are different types of activation functions,
Right.
each with its own strengths.
Okay.
You've got the sigmoid function, which squishes outputs between 0 and 1.
Okay.
That's often used for binary classification,
Uh-huh.
like deciding if an email is spam or not.
Makes sense.
Then there's real U, which is great for deep networks, and softmax for multi-class classification.
Okay.
Each one helps the network model different types of relationships in the data.
It sounds like choosing the right activation function is an art in itself.
It really is an art.
Yeah.
It's all about understanding the nuances of your data and the problem you're trying to solve.
Okay, so we've got this layered architecture,
Right.
these neurons with their activation functions.
Yeah.
But how does a neural network actually learn? Where does the training come in?
Training is where we teach the network to perform a specific task.
Okay.
Imagine you're teaching a child to ride a bike.
Right.
You give them instructions,
Uh-huh.
they fall,
Right.
you give them feedback,
Yeah.
and they try again.
Got it.
It's a similar process with neural networks.
So we're not explicitly programming the network with rules.
No,
It's learning from data.
exactly.
Wow.
The learning process relies on 3 key pillars:
Yeah, what are they?
forward propagation,
Okay.
loss functions,
Loss functions.
and something called back propagation and gradient descent.
Let's break those down.
Okay.
What's happening during forward propagation?
Remember that layered structure we talked about?
Ah.
During forward propagation, data flows through the network layer by layer.
Right.
Each neuron processes its inputs,
Okay.
and the output from one layer becomes the input for the next.
So it's like a chain reaction
It is.
with information cascading through the network.
Yes, and at the end, the output layer produces a prediction.
Okay.
This could be anything like identifying an object in an image,
Right.
translating a sentence, or predicting a stock price.
So the network makes a guess
Yeah,
based on the data it's seen,
right.
but how do we measure how good or bad that guess is?
That's the job of loss function.
Loss function.
They quantify the difference between the network's prediction and the actual value. There are different loss functions for different types of tasks.
So it's basically calculating how wrong the network is.
Exactly.
Okay.
The goal of training is to minimize that loss,
Right.
to make the network as accurate as possible.
And how do we get the network to improve its accuracy?
Right.
How does it learn from its mistakes?
That's where back propagation and gradient descent come in.
Okay.
That propagation is like a detective.
Okay.
It figures out how much each neuron contributed to the overall error. It traces the error back through the network layer by layer.
So it's identifying which neurons need to be adjusted.
Precisely.
Okay.
And then gradient descent uses that information to adjust the weights of the connections between neurons.
So it's like fine-tuning the network.
It is.
Nudging those weights in the right direction to reduce the error.
Exactly.
Wow.
It's an iterative process, repeating these steps over and over, gradually improving the network's performance.
This is incredible. We've covered the basic anatomy and training process of a neural network.
Yeah, we have.
But it sounds like there's a whole family of different types,
There is.
each with its own unique structure and capabilities.
Absolutely.
Let's dive into that next time.
Sounds good.
We'll pick it up there next time.
All right, see you then. Welcome back.
So we were just about to dive into the different types of neural networks.
Right.
You mentioned that there's a whole family of architectures.
There is.
Where should we start?
Let's begin with the simplest type, the feed-forward neural network,
Okay.
or FNN.
FNN.
It's like a one-way street for information.
Okay.
Data enters the input layer, flows through the hidden layers, and exits through the output layer.
So no loops, no feedback.
No loops, no feedback, straightforward.
Got it. What kind of tasks are FNNs good for?
They're workhorses for tasks like basic classification and regression.
Okay.
Think of predicting whether a customer will click on an ad,
Right.
or estimating the price of a house based on its features.
So pretty simple stuff.
Yeah, relatively simple.
Got it. So what about those convolutional neural networks we keep hearing about, CNNs?
Right.
What sets them apart?
CNNs are masters of visual data,
Right.
like images and videos. They have these special layers called convolutional layers,
Right.
which act like filters that scan the data for patterns.
Filters. Can you give us a visual?
Imagine a magnifying glass scanning a picture.
Okay.
That's kind of what a convolutional filter does.
Mhm.
It slides over the image looking for specific features,
Okay.
like edges, corners, or textures.
So they're breaking down the image
Yep.
into its basic building blocks.
That's a good way to put it.
But images can be huge.
They can.
How do CNNs handle all that data?
They use pooling layers to downsample the data,
Okay.
making it more manageable without losing those important features.
So they're extracting the essence of the image,
Exactly.
the information that really matters for the task at hand.
That's right.
And that's why CNNs are so powerful for image recognition,
Yeah.
object detection, and even medical image analysis.
All sorts of visual tasks.
Incredible. Okay, on to the next type day. Recurrent neural networks,
Oh.
or RNNs. I know they're all about sequences.
They are? How do they work?
RNNs have loops
Oh.
that allow information to persist. Think of it like having a short-term memory.
Okay.
They can process sequential data, like time series or text, by remembering what they've seen before.
So they're taking the context into account,
Exactly.
not just looking at each piece of data in isolation.
Right.
Makes sense. What kind of applications are they used for?
RNNs are the brains behind things like language translation,
Okay.
speech recognition,
Uh-huh.
and even generating music.
Wow.
They're amazing at anything involving sequences.
Speaking of language, I've heard a lot about transformers lately.
Yeah, transformers are really interesting.
Are they related to RNNs?
They're both used for processing sequences,
Okay.
but transformers are a newer type of architecture.
They've been revolutionizing natural language processing with their ability to understand long-range dependencies in text.
Long-range dependencies, what does that mean?
Think about a sentence with a pronoun at the end.
Okay.
Like, the cat sat on the mat and it was very comfortable.
Right.
To understand what it refers to, you need
Yeah.
to go back to the beginning of the sentence.
Right.
Transformers are really good at making those connections, even across long distances.
That makes sense. So they're kind of like superpowered RNNs.
In a way, yes.
Okay.
They use a mechanism called self-attention,
Okay.
which allows them to weigh the importance of different words in relation to each other.
And this has led to those impressive large language models we keep hearing about.
Exactly. Transformers are powering things like chatbots,
Right.
language translators, and even code generators.
Wow.
They're pushing the boundaries of what AI can do with language.
This is also fascinating. We've got these different types of neural networks,
We do.
each specialized for different tasks.
Right.
It's like a toolbox for AI. But with all this power comes responsibility, right?
Absolutely. As with any powerful technology, we need to think about the ethical implications.
Like the potential for bias in the data.
Yes.
So the impact on jobs.
Those are definitely important considerations.
Yeah.
We need to ensure that AI is developed and used in a way that benefits everyone.
Well said. Now let's shift gears for a moment
Okay?
and explore some of the groundbreaking applications of neural networks.
Right.
I'm particularly intrigued by their use in healthcare.
Me too. The potential for AI to revolutionize healthcare is immense.
I've heard about systems that can diagnose diseases from medical images with remarkable accuracy.
That's right. CNNs are being used to analyze X-rays, CT scans, and MRIs,
Wow.
helping doctors detect conditions like cancer, pneumonia, and eye diseases
Right.
earlier and more effectively.
Early detection is so crucial.
It is.
For successful treatment, are there other ways AI is being used in medicine?
Absolutely. Neural networks are helping to personalize treatment plans.
Okay. Predict patient outcomes
Wow.
and even discover new drugs.
So it's not just about diagnostics, it's impacting the entire healthcare landscape.
It really is.
This is incredible. What about other fields?
Let's see.
What are some other exciting applications?
Well, in the realm of autonomous vehicles, neural networks are playing a crucial role.
They're the brains behind self-driving cars, right?
Precisely. They process data from sensors
Right.
like cameras, LiDAR, and radar
Uh-huh.
to perceive the environment, make decisions, and navigate safely.
It's amazing to think that machines can now drive themselves.
It is pretty amazing.
And it has the potential to make our roads safer and more efficient.
It does.
And what about creative fields?
Oh, yeah.
AI is being used to generate art and music.
That's right. Systems like DALL-E can create stunning images from text descriptions.
Right.
And Jukebox can compose original music in different styles.
It's blurring the lines between human and machine creativity,
It is.
opening up a whole new world of artistic possibilities.
So we've seen that neural networks are impacting everything from healthcare to transportation to the arts.
Yeah.
It's a truly transformative technology that's touching every aspect of our lives. But it's not all sunshine and roses, right?
You're right.
There are challenges and limitations too. Let's explore the other side of the coin.
Okay, let's do that.
Yeah.
Yeah, it's true that as much as there is to be excited about, there are some challenges too. Not every application of this technology will be a good one.
Yeah, that's an important point. We can't just blindly embrace any new technology without considering the potential downsides. You mentioned earlier that one of the big challenges with neural networks is this black box problem.
Yeah.
What's that all about?
Well, neural networks can be incredibly complex.
Right.
It's often difficult to understand exactly how they arrive at their decisions.
Right.
Even the people who design them, may not be able to fully explain the inner workings.
So it's like they're making these decisions behind a curtain. And we're just left wondering how they got there.
Yeah.
That could be a problem.
It could?
Especially in situations where trust and transparency are critical.
Absolutely.
Like, think about a medical diagnosis made by an AI system.
Right.
You'd want to know why the system reached that conclusion,
Yeah,
what factors it considered.
exactly.
The same goes for things like loan applications
Yeah,
or even self-driving cars.
for sure.
So how can we address this black box problem? Is there any way to make these systems more transparent?
Well, that's a big focus of research right now.
Okay.
Scientists are developing techniques like explainable AI or XAI to shed light on the decision-making process.
So it's like giving these black boxes a window
Yeah, like opening them up.
so we can see what's going on inside.
Exactly. XAI aims to provide insights into why a network made a particular decision,
Okay.
what factors were most influential, and how those factors interacted.
That sounds promising.
Yeah, it's a really interesting area of research.
What about other limitations?
Mm-hmm.
I know data bias is a big concern with AI in general.
Oh, absolutely. Neural networks are only as good as the data they're trained on.
Right.
If the data is biased, the network will inherit those biases,
Right.
leading to unfair or discriminatory outcomes.
So it's not just about the technology itself.
Right.
It's about how we use it
Yeah,
and the data we feed it.
the data is key.
We need to be very mindful of that.
We do, and that brings up another issue.
What's that?
The sheer amount of data these models require.
Right.
Training large neural networks can be incredibly data-hungry and computationally expensive.
I've heard it can take massive amounts of computing power,
It can.
which raises concerns about energy consumption
Yeah.
and the environmental impact.
Those are definitely important considerations.
Yeah.
Researchers are working on making these models more efficient,
Right.
but it's a trade-off between performance and sustainability.
So we've got these challenges to address,
We do?
but the potential is undeniable.
Oh, the potential is huge.
Where do you see neural networks heading in the future? What's on the horizon?
Oh, the future is incredibly exciting. One area that's really heating up is neuromorphic computing.
Neuromorphic computing.
We're talking about building hardware that mimics the brain's structure and function.
So like artificial brains.
In a way, yes, these neuromorphic chips could lead to much more efficient AI systems
Wow.
that learn in real time, just like our brains do.
That's mind-blowing. What else is cooking in the AI lab?
We're also seeing breakthroughs in spiking neural networks.
Spiking neural networks.
These networks model the way neurons communicate,
Okay.
using spikes of electrical activity just like in the biological brain.
So they're even more biologically inspired.
Yeah, they are.
What kind of applications could that lead to?
Think about robotics, brain-computer interfaces.
Right.
Anything that requires real-time processing and adaptation to a changing environment,
Yeah.
spiking neural networks could be game changers.
This is also fascinating. It feels like we're on the cusp of a whole new era of intelligence,
It does feel that way.
where the lines between human and machine are blurring. It's exciting,
It is.
but it also raises a lot of questions.
It does, and that's why it's so important to have these conversations,
Right.
to think about the ethical implications, the potential risks, and how we can steer AI in a direction that benefits humanity.
It's a shared responsibility for sure.
It is.
We all need to be part of the conversation. Well, this has been an incredible journey exploring the world of neural networks. We've covered a lot of ground from their biological inspiration to their transformative applications and the challenges they present.
It's such a dynamic and rapidly evolving field. There's always something new to learn, always a new breakthrough around the corner.
That's what makes it so fascinating. Thank you for joining us on this deep dive into neural networks. We hope you've learned something new and that you'll continue to explore this incredible field.
And remember, the future of AI is not predetermined. It's something we shape with our choices and our actions. Let's make those choices wisely.
Thank you for tuning in to the History of AI podcast.